Okay, Bismillah ar-Rahman ar-Rahim. As-salatu was-salamu ala Rasulillah. You see, as you can add the two vectors to get a resultant, similarly, you can also resolve a vector into its components. What I mean to say by that, suppose this is a table, top of the table. You can apply one force, one person can apply the force here by his hand, and another one can apply the force here by his hand. Now, where this, in which direction this table has tendency to move, that you can find out by adding these two vectors by law of parallelogram. So here, so they will be added over here. So this you can move on this place, and this you can move on this here. Sorry. So you will get the resultant here. So it means effectively this table is experiencing a force in this direction, which I am showing here by this arrow. So this table has tendency to move in this direction. Okay. Yes, Muhammad.
Yes, Doctor. We can even do it by triangle, right?
Yeah, you can do it by triangle also, no problem. Yeah. So, but as I said, in case of triangle, sometimes you may lose the line of action of the forces. But in case of parallelogram, line of action of the forces are preserved. So this table has tendency to move in this direction. Okay. So this is called resultant of these two vectors. It means these two we can replace by single this one. Now, exactly the same way, you can have opposite situation. If this table is subject to a force like this, okay, so this will try to move this table in this direction where the force is acting. So this will be equivalent to, if you remove this one and apply two forces of this and this type. So these two forces will give the same effect as this force alone. So then these will be called as components. Okay. So components and resultant, they are very much linked together. Like here in this figure, this is the force, okay, which is the resultant of this and uh, please make it as somebody has increased this because what happened? Yes. So 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 any two or more vectors whose sum equals a certain vector are said to be the components of that vector. So summation of vector fx and vector fy is equals to vector f. This is by a law of parallelogram because you are putting these two vector fx and vector fy over the two sides of parallelogram. So their resultant is vector f. So vector f will be called as the resultant of vector fx and vector fy. On the other hand, vector fx and vector fy, they will be known as the components of vector f. So components and resultant are like father and sons. So you can say that vector fx and vector fy are sons of vector f. And vector f is a father of vector fx and vector fy. Okay. So the vector fx and vector fy are the components and vector f is the resultant. Okay. Now if the angle between the two components is 90°, then in that case, these components are known as rectangular components. So we will call rectangular component when the angle between the two components is 90°, or when the components are perpendicular to each other. Like here, this theta equals to 90°. So vector fx and vector fy, they will be known as rectangular components of vector f. On the other hand, if you have the components like this, where the angle between the two components is not equals to 90°, then we call them non-rectangular components. So for the same resultant, you can have rectangular as well as non-rectangular components. For example, if suppose this is a vector, okay, now you are taking the, let me change the color, rectangular components, so they should represent the two sides of a parallelogram. So this is this. So this is, these two are the rectangular components. Now if I go and take a blue color, so you see here, those which are shown by the purple color here, they are the rectangular components of this vector. And those which are shown by the blue sky color, they are the non-rectangular components of the same vector. So for the same vector, you can have rectangular components as well as non-rectangular components. Okay? But from calculation points of view, handling rectangular components are much easier compared to non-rectangular components. So as far as possible, we try to have rectangular components rather than non-rectangular components. Okay? But there are situations when you will be bound to have the non-rectangular components. But as far as it is possible, try to avoid non-rectangular components and you take the rectangular components, because that is much easier when you will be doing the analysis of force system. But here, as you can see, vector f is equal to vector fx plus vector y, and this is equal to vector f1 plus vector f2. And it is very clear that these two non-rectangular and rectangular components of the same force vector, they are not equal. First thing, they will be, as I have shown over here, that they are different in magnitude, as you can see here, and also they are different in directions. Okay, so they are not equal to each other magnitude wise as well as the direction wise, but both are giving the same result. It means their vector sum is the same. So if this is vector f1 vector, vector f1 plus vector f2 equal to vector f, and if it is fx and fy is equal to vector fx plus vector fy is equal to vector f. So these two terminologies keep in mind, because we will use many times rectangular and non-rectangular. So when we say rectangular component, it means the components, the angle between the components is 90 degree, and when we say non-rectangular components, it means the angle between the components is not 90 degree. And in this case, non-rectangular case, we use sine law and cosine law in general for the analysis of forces. Now I come to a very important vector, which we will use frequently in this course, that is called unit vector. Okay. Anybody has idea what is a unit vector? Yes, Mr. Muhammad.
It's a vector that has the same direction of the real vector, but
Okay.
magnitude is 1.
Yes, very good. Very good. Because unit vector is always of some vector. Okay. So for example, if I say unit vector of vector A, that means it is having the same direction as the vector A. But magnitude wise, its magnitude is unity, and that is dimensionless. So if I make a figure, for example, if this is vector A, then in the same direction, this is another vector, which I can call as vector NA. So this vector NA and this vector A, both are acting in the same direction. So, but the magnitude of this vector is unity. Anyone can tell me what is the use of unit vector? Why do we need unit vector?
To have
Yes. Yes,
find
yes. Yes.
to find
To find it. Actually, whenever you have a magnitude and you want to convert this magnitude into vector, you need to multiply it with a unit vector. For example, if this is a force, for example, if you see here, if this is a force of say 500 Newton, and you want a vector, so you need to multiply the unit vector in this direction. For example, if this is acting in the positive x direction and the unit vector is I, so just we have to multiply these two to get the force vector. So you will be able to get the force vector. So with the help of unit vector, you can convert a magnitude into vector form, okay, analytically. All right. So mathematically, we define the unit vector by dividing a vector by its magnitude. For example, here you can say vector A we are dividing by its magnitude. Either you will write like modulus or write without showing any arrow. Both represent the magnitude. So vector A divided by A, that is the unit vector. Okay, because you can write like this: if A is the magnitude of vector A, then Wahid will be the magnitude of vector A into Wahid divided by this A. So unit vector is the one which has the magnitude Wahid unit. So this is the unit vector. Okay. So unit vector is dimensionless, it has no unit. And second, the direction of the unit vector is the same as vector A. There are 6 standard or Cartesian unit vectors which represent the 6 directions in the space, and those directions are positive x, positive y, and positive z, and then negative x, negative y, and negative z. So for positive x direction, the unit vector is I. We write it like this, or we write it like this. And the positive y direction, the unit vector is j, or we write it like this, j cap. And similarly, in the positive z direction, if this is the in the positive z direction, if this is the z direction, we have unit vector k. We write it like this, or you can write like this. Okay. And similarly, we have in the negative x direction the unit vector minus I, in the negative y direction minus j, and in the negative z direction it is minus k. So this way we have the 6 unit vectors, plus I, plus j, plus k, and minus I, minus j, and minus k. They are the standard unit vectors or Cartesian unit vectors. So if you have a force, suppose this is the z direction, this is x direction, this is y direction. All right. Here x direction does not mean that it is like a triangle. Actually, it means it is facing you, okay? One of the axes. Okay? So let us talk in terms of two dimensions. So this is x direction, this is y direction, for example. And if we have a force of 300 Newton acting in the positive x direction, now if somebody wants to know what is the force vector, so how much will be the force vector? In terms of unit vectors. You see, this is the force which is acting in the positive x direction. All right, because this is our, they don't see this one for the time being. Okay, so this will be equals to what? Unit vector in the positive x direction is?
It's 300 multiplied by
300 multiplied by?
I.
Yes, very good. So this is the force vector. Similarly, if you have a force acting in the positive y direction, and say this is 450 Newton, and you want to write it like a vector, so you can write 450 g. So similarly, if a force is acting in the z direction, you can multiply by k, and it will convert into vector. So if the forces are acting in the positive x, positive y, positive z, negative z, they are very easy. It is very easy to convert them into vector form. But if suppose it is acting in a direction which is neither x nor y nor z, for example, this is the direction. Sorry, I'm not able to make the drawings properly. Now suppose this is the force of 30 kilonewton, and I want to convert this into vector form. So how will you do now? Say this angle is given to you 30 degree.
It's 30 multiplied by 30 cosine. No, sorry. Multiply by yes, 30 cosine theta plus 30 sine theta over square root of 30 cosine square plus 30 sine square.
No, actually, that must first part is your answer is correct. What you will do in this case, you will try to have its components in x and y directions. So this will become, this I will discuss later in detail, 30 cosine 30, and this will become 30 sine 30. Okay. Now you multiply this because in this direction, you know the unit vector, that is I, okay? And multiply this, because you know in this direction, unit vector is J. So you multiply by J, okay? Then this factor, then your force vector will be simply summation of this and this, as per parallelogram law, this and this, because this is the resultant of that. So you will have 30 cosine 30I plus 30 sine 30 J. So this is how we have got the force vector for the situation when it is acting in some other direction. Neither it is not acting in the direction of x, y, or z. So in this case, you can resolve this, the forces, into its components, and then you can convert them into vector form by multiplying appropriate unit vector, and then sum them, you will get the vector. Okay. So this is the use of this standard or Cartesian unit vectors. So here, if you see, I have given an expression. This is for 3 dimension. So if you have a vector A, you can take its components in x, y, and z directions. So they are ax, ay, and az, and then multiply them with their unit vectors. So ax is acting in the positive x direction, so ax into I will be the vector. Ay is acting in the positive y direction, so ay into j, and az is acting in the positive z direction, so az into k, and then you add them together, you will get the vector. Okay, so this is the vector in a component form with the help of unit vectors. Direction cosines. Direction cosines we use mainly in the 3 dimension problems. Okay, what is the direction cosine? You see, if this is a vector, if this is the red color is a vector which is making an angle of theta x with the x-axis, theta y with the y-axis, and theta z with the z-axis. Okay. Then if you take cosine of theta x, cosine of theta y, and cosine of theta z, they will be known as direction cosines of vector A. Okay. So cosine of theta x, cosine of theta y, and cosine of theta z will be known as the direction cosines of vector A. For example, let's take in 2 dimension. Suppose this is a force of magnitude 50 Newton, and this is your x-axis and this is your y-axis. And this one is making an angle of 40 degree, and this one, is there a problem in hearing?
No, good.
Okay.
I'm asking for something to my classmates.
Okay. So this is 40
Thank you.
degree, so this will be definitely 50 degree. Okay. All right. Now, if I ask, what is the direction cosines of this 50 Newton? So how much will be direction cosines? Of 50 Newton? Direction cosines, how much angle it is making with x, y, and z axis?
50 Newton multiplied by cosine 40.
No, that is not direction cosine. Direction cosine will be simply cosine of 40 degree. This is the first direction cosine, which we generally denote by L. And direction cosine, another second direction cosine will be M. That is cosine of 50 degree. because this is making an angle of 40 degree with x-axis. So cosine of 40 degree is the first direction cosine, and it is making an angle of 50 degree with the y-axis. So cosine of 50 degree, that is the second direction cosine. Of course, it is a two-dimension problem, so we have only two direction cosines. But in three-dimension problems, you will also have an angle with z-axis. So that will be then the cosine of that will be the third direction cosine. So this way we have, like here in this problem, if this is x-axis and if this is making angle of theta x, this is theta y, and this is theta z. So cosine of theta x, cosine of theta y, and cosine of theta z, they are equals to L, M, and N, and they are known as direction cosines. Okay. Is it clear, boys? What is direction cosine? Like here also I have shown here theta x, theta y, not the component. I'm talking about the direction cosine only. So cosine of theta x, cosine of theta y, that will be the direction cosines. Now there is a relationship that exists between the direction cosines, and that relation is this one. L square plus m square plus n square equals to 1. Okay. So remember this one because sometimes we use this expression. So it means if you know the two direction cosines, third direction cosines you can get by this expression. For example, if you know the cosine theta x, that is L, you know the cosine theta y, that is M, then you can get the cosine theta z by this expression. Keep in mind here n we are using as a for direction cosine, because this n might be confusing to you sometimes, because n also we use for unit vector and n also we use for direction cosines. So you have to see the context, that whether we are talking about the direction cosines or we are talking about the unit vector, because generally vector n we use for unit vector and only n we use for cosine theta z, that is direction cosine. Okay. Now once you know the direction cosines, you can write the components in a very, very easy manner, because if this is theta x, so component of this this component will be equals to a cosine theta x, because if the magnitude of this is a, so this will be a cosine theta x. Exactly same way here, this will be equals to a cosine theta y. And why it is like that, let me tell you, because maybe you see if this is a magnitude of 50 Newton and this is say theta. So if you take cosine of theta, so cosine, and this is I'm calling as fx, and this you can call as fy. So cosine of theta will be this upon this, and this total I am calling as f. So fx upon f. So fx will be equals to f cosine theta. Okay. So this will be f cosine theta. If I express this by theta x, so this will become f cosine theta x. All right. Yes, boy, you want to ask something? So this is f cosine theta x. So, and similarly, for this part, if I say theta y, so again you take the cosine theta y. So what will happen? You will have fy over f. So fy over f will be equals to, so it will give fy equals to f cosine theta y. So what I conclude here, that on angle side, always on angle side, it is the cosine component. So if this is the angle, so this will be f cosine theta x. If this is the angle, then it will be f cosine theta y. But of course, you can express this also with the help of this angle. if you take the sine theta x, then it will be equals to Fy divided by F. So Fy equals to F sine theta y. So that is also possible. But here we are not doing that one, because here we are having the angle with axis. So theta x is with the axis. So so if this is A, so this will be A cosine theta x. This is with the y-axis. So this will be A cosine theta y. So if you know the direction cosines and you want to find out the components, so simply you multiply each direction cosine with the magnitude of the resultant force or resultant quantity, you will get the components. Like here you can see it is A cosine theta x. Okay, because this angle with x is theta x, so A cosine theta x, AY will be A cosine theta y, and AZ will be A cosine theta z. And of course, if you take the summation of their square, then it will be equals to the value itself. And if you want to find out, if you want to express it in the vector form, then it will be vector A equals to AXI plus AYJ plus AZK. Somebody is putting his fingers on this. Please remove it. Yeah. So this is equals to, in the place of AX you can write A cosine theta, and in the place of AY you can write A cosine theta y, and in the place of AZ you can write A cosine theta z. So you will have A cosine theta xi, A cosine theta yj, and A cosine theta zk. So A you can take common, and in the place of cos theta x, cos theta y, and cos theta z, you can substitute L, M, and N. So this will become A Li plus Mj plus Nk. So vector A will be equals to A into Li plus Mj plus Nk. Okay. So anyone can guess what is this quantity? Li plus Mj plus Nk.
Direction vector.
Anyone? Pardon?
Direction vector.
Direction vector. Actually, there is no like direction vector. This is basically, if you see here, this is vector A divided by A. Am I right? This will be equals to Li plus Mj plus Nk. So this is nothing but your unit vector. Am I right? Because vector A divided by magnitude is the unit vector. So this term represent nothing but unit vector. So this more we will discuss later, inshallah. So this is the use of the direction cosine. That with the help of the direction cosine. Excuse me, boys. Somebody is Somebody is moving his finger over the screen. Please move. Get out from here. This is very disturbing. Like this finger. Who is doing this one? Okay, so this is direction cosine. So direction cosine is not a big deal. Just you have the angles with the x, y, and z axis. You take the cosine of that. That will be called direction cosines. Okay. And we represent them by L, M, and N. And there is a relationship that exists between these direction cosines. That is L square plus M square plus N square is always equals to 1. And with the help of direction cosines, you can write the components very, very comfortably. That simply you multiply with the magnitude of the total, like A cosine theta x, A cosine theta y, A cosine theta z. That will be the magnitudes of your your vector quantity, components of your vector quantity in x, y, and z directions. Now I come to the scalar multiplication and division. You see, there is a vector multiplication which I will discuss after this. Okay. Here we are talking about the scalar multiplication. It means if you have a vector and you multiply this vector by a certain value like 2, 3, 4, 5. So what will happen to that? Like, for example, if this is vector A and this is vector 2A and this is vector 3A, 3 vector A. Anyone can tell me what is the difference between these three vectors? Vector A, vector 2, 2 vector A, and 3 vector A. What is difference between vector A and 2 vector A and 3 vector A?
Doctor, vector
Yes?
A smaller than 2A.
That is true.
Yeah, 2A bigger than vector A.
Yeah, a 2 vector A means simply you are doubling the magnitude of the vector, keeping the same direction. It
Yeah.
means, yes, if you have, this is say graphically, if I show, if this is vector A, then 2 vector A means it is the same vector but double in magnitude. Similarly, 3 vector will be 3 times vector A. And the same thing, same principle applies if you take the division. Like if you divide by 3, it means this is also this having the same direction as vector A, but its magnitude is 1/3 of vector A. So graphically, if I show, it may be like this one. So it has the same direction as vector A, but magnitude wise, it is 1/3. So this is vector A divided by 3, or 1/3 times vector A. So this is called scalar multiplication and scalar division. So by scalar multiplication and division, simply either you magnify or increase the magnitude of the vector, or you decrease the magnitude of the vector, okay, by multiplying or by dividing. Yeah, next is the vector multiplication, and this is one of the very important multiplication which we will be using in this course. You see, when you are going to multiply the two vectors, let me discuss here, there's a space here. Your answer may be a scalar or a vector. For example, if you multiply force with the displacement, that is vector F and vector D, what is the answer? Anyone knows? Multiplication of the force and displacement, it is equals to how much? It is equals to work. Very good. So this is equals to work. And as you know, work is a scalar quantity because it's an energy only. A scalar quantity. On the other hand, if you multiply a position vector, this I will discuss later, and force vector, your answer will be moment m. Okay. In this case, this is vector, but the answer is a vector. However, here it was a scalar. So when you are multiplying the two vectors, your answer may be scalar, your answer may be vector. So depending on what is going to be your answer, we decide the sign of multiplication. As you know, the sign of multiplications are two, very common. Sign of multiplication. One is this dot and another is this cross. Like if you want to show A into B. Or if you want to show 2 into 3. So multiplication either you can show by dot or you can show by cross. So when your answer is going to be scalar, that multiplication we will be representing by dot, and when your answer is going to be a vector, that multiplication we are going to write by cross. So by seeing the dot or cross, you will become able to know that whether the final answer is a scalar or a vector. Okay, inshallah, we'll continue this in the afternoon class.